Hey guys, welcome back. We're going to introduce MO theory a little bit here. We'll talk about orbitals and molecules and how they bond. And we want to talk about this a little bit. We don't go that much into MO theory because we don't really just need to. So when two atoms form, the electrons in the bond are under the influence of two nuclei, and therefore lower in energy than they were in the individual separate atoms. The electrons now occupy an orbital that belongs to the molecule. So it's when two atoms combine, their orbitals, since we're treating these electrons as waves, right? So we step back, what's quantum mechanics? Treating the electron and using the electron's wave-like characteristics to predict the behavior of the atom, behavior of the electrons, and behavior of molecules. So now when two atoms combine, we no longer have individual atoms with one nuclei. We have more than one nuclei with more than one electron and all these interactions. The math gets really, really complicated. Of course, we're not even touching the math. But the orbital that's formed is a new orbital for the molecule. And we look at these molecules and the orbitals because we care about where the electron density is. That's where the bonding happens. Where are the electrons at? So where are the bonding opportunities? How do we build more molecules? How do we take atoms off of molecules? All that stuff becomes important when we design a molecule, because all sorts of things are done for designing, from like vaccines to compounds that mimic opiates that are not as addictive, to uh, substances like better glass for your phone, to better cases for your phone, and the list goes on and on and on, right? It doesn't end. So we need to understand, if you're going to be doing this, how these electrons are so that we can predict behavior and predict how to do things. So back to the basics now, back to the small little picture of two atoms bonding, right? In order for these atoms to combine, or the atoms to bond and the orbitals to combine, they have to have similar energies. They have to overlap. So they have to overlap in the same space and have the same symmetry, which means they have to be the same phase. So if you look at just graph y equals sine x, y equals positive sine x has a slightly different shape than y equals negative sine x. And what's slightly different about it? Well, they look the same, they're just mirror images. Exactly. So if I go up first, positive sine x, then down, versus going down first, then up, negative sine x. So sine x plus sine x will be in the same phase. Negative sine x plus negative sine x will be in the same phase. However, sine x plus negative sine x would equal 0. So that's what we're talking about. So they have to be in the same phase. So it has to be going up first, or it has to be going down first, so to speak. Right? So that's when we say the same symmetry, that's what we're talking about. And so they have to be in the same, they have to overlap in space, have similar energies, and have the same symmetry. So let's just take about a simple diatomic molecule like H2. All right, two atoms in a larger molecule as well, but let's just focusing on the first, just two atoms, H2, N2, O2, doesn't matter. The quantum numbers that characterize the orbitals are, in blue for the one atom, you got a principal, you got a secondary, and you got M sub L, from negative L to positive L. Once we get to two atoms or more, still principal energy level, now we have a secondary, they call it lambda, and we get these new shapes: sigma, pi, delta. Sigma, pi, delta. All right, sigma still is only 1, and it's going to be on, this is very important, it's going to be on the internuclear axis. The pi bonds are going to be off the internuclear axis. What is the internuclear axis? That would be put a line through two nuclei. That's the internuclear axis. It could be X, Y, Z, however we define it. Delta bonds, It only happens in metals. It's the fourth bond. So the first bond is always going to be a sigma bond. The second and third bonds are pi bonds, and that's where we'll stop. We won't do any delta bonds. They do exist, just they're not as common, and they happen in metals. So sigma pi, sigma pi pi, sigma pi pi. Right, that's your combinations. The other combinations, so that's a single bond, right? Is always sigma's first, second, third, first, second, third, fourth. However, in space, what do we have to combine? Right? What are my possible combinations? Well, I can have a sigma plus a sigma, right? I could have, well, let's talk about that. Let's a sigma bond. What makes a sigma bond? It can be S plus an S. It could be an S plus a P. It could be a P plus a P. It can all equal a sigma bond. But however, they have to be on the internuclear axis. So whatever, I'm just going to make it red. Axis. So if it's px, if the internuclear axis is x, px. If the internuclear axis is y, then it's py. That has to be on the axis. And then for pi bonds, p, all right, plus p, or p plus d can be pi. Now, these are very important. This has to be the same. So whatever that p orbital is, this p orbital has to be the same. So px and px, py and py, pz and pz. That's what I'm saying. So px plus px, or py plus py, pz plus pz. Those are all good. Not good would be px cannot plus py is a no. That can't happen. They don't overlap in space. Same thing down here. The P down here has to have some type of overlap with the D's to make a pi bond. So what do these look like? Well, let's give you pictures. And so when we talk about, like, if right now we're going to say the internuclear axis is X. So when we draw our XYZ plane, X, Y, Z, X is the internuclear axis. So you got px plus px, they combine, and you can see the bond is right here. You have an atom and an atom. So the sigma bond is in between those two atoms on the internuclear axis, on the x-axis. Z here, so we're going to say this is PZ and PZ because it's vertical in our little picture. So again, there's an atom and an atom. So there's my atoms. So if you notice the sigma bond right here, the sigma is right there between the two nuclei. And the pi bond, this is weird looking shape, is the pi bond is above and below the plane. It could also be left and right. So if it was py and py, it would be left and right of the sigma bond instead of above and below. These things can rotate in space. So there's an internuclear axis. Let's just call it X again. So there's X. And so if you were to look down, let's say I was going to put my eyeball right there. You got your nice lashes. All right, we look down. What would I see? I would see sigma bond, and I could see kind of, there's my pi bond above and below. The pi bond could be, left and right as well. So it could be there as well. So that's what we're looking at. Just looking at this three-dimensionally in space. It's not as, I guess, straightforward as other things because it's very abstract and you have to visualize, and that's a skill that most of us don't work on in our daily lives. Some of you guys are better than that than others, but we're still not always working on it and developing it, and that's okay. If we come back to this MO theory, let's look at a few MO diagrams. So H2, right? We have two hydrogen atoms, and it's 1s1. So this is important, two atomic orbitals make two molecular orbitals. So what does that look like? So if I have a just energy diagram here. So that's just energy. Oh, I don't want two heads. I'm sorry. Draw one-headed arrow up. So our chemical potential energy. I would have an H, H2, H. They start with 1s. So right here, let's just say that's my 1s orbital for this hydrogen and my 1s orbital for that hydrogen. And they both have one electron in the 1s orbital. When they mix, right, we have the wave can be going up or the wave can be going down. So when these two atomic orbitals mix, they're going to have one that's in phase, a mixing that's in phase, and a mixing that's out of phase. Like a sin X and a sin X, and a sin X minus sin X, so to speak. So the one that's in phase for H2 would be the sigma bond, right? And we call that bonding. And it's the sigma 1s. And the out of phase is the sigma star 1s, and then we call that anti, if I can spell, anti-bonding. And so a lot of times you'll see these little dotted lines to let you know that these orbitals are those two that are mixing. And so what happens here is these two electrons each go now into the molecule down there. So why? Why do we do that? This electron's going in, and this electron's going in. So we got the free atoms versus the molecule. And so these electrons will go to the molecule and fill up the molecule, just like we've done before with the electron configuration. So that's hydrogen. And so this 1s, let me get it purple, perfect. This is lower in energy. Due to constructive interference. And this one is higher in energy due to destructive interference. That's wonderful. So bonding, antibonding. So sigma comes from the shapes of the orbital. It's the same as valence bond theory. It's still a circle. All right. And that's the MO diagram for H2. So what does this mean? We can approximate the MOs as basically a linear combination. That's what we're doing, is a linear combination of atomic orbitals. And the total number of molecular orbitals formed is always equal to the number of atomic orbitals. And when atomic orbitals combine to form molecular orbitals, one molecular orbital is always lower in energy and one is higher in energy. The lower energy one is debonding, the higher energy one is antibonding. When assigning electrons to the molecular orbitals, we always throw the lowest energy first, and Hund's rule applies. Here are some period 2 examples. If we look at B2, C2, and N2 as diatomic molecules, and O2, F2, and Ne2, right? These are how the orbitals form. So you have the atomic orbitals. One on each side would represent like B or C or N. So if I have B2, I'd have one boron and another boron. Well, how many electrons does borons have that are valence? Well, boron has two core electrons, 3 valence. The core is not shown. That would be the 1s, like we just did with hydrogen. So blue boron has 3 valence electrons, 1, 2, 3. And orange boron has 1, 2, 3. When they mix, I have 1, 2, 3, 4, 5, 6. So one boron, and 2, 3, 4, and then Hund's rule applies. 5, 6. That's supposed to be purple. It's purple. There we go. There's B2. Now the difference between B2 and O2 or F2 is that sigma is lower than pi, and sigma star is higher energy than pi. So this is out of order for boron, carbon, and nitrogen. It's just out of order. And that has to do with large P and S interaction. So the 2S and 2P really interact in B, C, and N, and they don't interact as much in O, F, or N, E. We'll do one more, and then we'll go from there. O2 here. So if we look at O2, we have a blue oxygen, and then I'll have a green oxygen. So the green oxygen has 6 valence electrons. 1, 2, 3, 4, 5, 6. Of course, the blue oxygen has 1, 2, 3, 4, 5, 6. And in orange, we'll do them together. So fill in 1, 2, 3, 4 full. Then we have 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. And that's O2's MO diagram, because the molecular orbitals would be for O2. That's the molecule. I want to point something out. So bonding, antibonding. There's something called bond order, and I'm not going to ask you the bond order at this point, but the bond order is how many electrons are in bonding orbitals versus how many electrons are in antibonding orbitals. And so you take the number of electrons in bonding minus the number of electrons in antibonding and then divide by 2. So in this case, what's the bond order? These two cancel out, so but 2, 4, 6, 8 electrons minus 2, 4. 8 minus 4 would be 4 divided by 2, 2. Double bond. That's where you get oxygen's bond order. One thing I do want to point out is that we have unpaired electrons. So oxygen is actually what we call paramagnetic. So it looks like all of oxygen's electrons are paired, but unpaired electrons usually give rise to paramagnetism, which means they will attract to a magnet. Boron is also the same way. It's paramagnetic. And valence bond theory does not give us a way to describe this. MO theory does, which is kind of nice. So there are limitations to valence bond theory, especially when we get to more than tetrahedral. Octahedral and trigonal, bipyramidal, they start to break down. Valence bond theory starts to break down how it's really working. MO theory does a better job with those. MO theory doesn't cover everything that valence bond theory does either. So they're both good theories. They have their limits, and they're both good to know. Valence bond theory is probably more important for you now. especially in Chem 1, Chem 2, and organic chemistry. And I'd say molecular orbital theory is probably more applicable to like transition metals. They all have their places, and that's good. So let's recap the B2, C2, N2, O2, F2, Ne2. And of course, Ne2 does not exist because the bond order is 0. That's MO theory. I'm not going to really hammer MO theory home to you guys. I happen to like it, but that's great. Doesn't really apply to you. Just know that I do sometimes ask what orbitals can overlap in space for certain atoms, and there will be questions like that that you can practice with. Otherwise, that's the bonding theories, and that's it for the video. Take care.